Hello and welcome to How to Understand X. Today we're going to be tackling derivatives, and before we get into any calculus, huge disclaimer, you're not going to fully understand derivatives in whatever arbitrary time limit I've put in the title. That was a lie, a falsehood. This is clickbait. The reason this is because derivatives and differentiation is essential to calculus. The understanding operations and usage of derivatives is essential to calculus. And I can't teach you all of calculus in like an hour or however long this takes. So what I'm going to try to do is contain myself and introduce you to what the derivative is and what it means within the context of single variable calculus, where it comes from, and where certain derivative rules and common derivatives come from as well. And perhaps in conjunction with those derivative rules, I think knowing those common derivatives will probably be enough to differentiate almost anything that you were going to have to do. But, I'm also going to do maybe some implicit differentiation and differential equations. But I'm hoping that this video serves as a relatively good introduction to what calculus itself is, and one of the most important operations in calculus being the derivative, and why that is. So, disclaimer, over. Let's talk about calculus before we get into any, conversations about differentiation. What is calculus? Well, like all studies of math, it is the study of one thing, and that one thing's properties and operations. For example, geometry is the study of shapes and their properties. And by extension, trigonometry is the study of triangles and their properties. And algebra is the study of mathematical operations and the properties of algebraic quantities. But calculus is unique. It is the study of continuous change. And I apologize for my handwriting. I am writing this freehand on a laptop screen. But yes, calculus is the study of continuous change. Well, I'm not sure about you, but to me, that's also pretty abstract. I have no idea what that means. If I were to define continuous change in as broad of a context as possible, I would say that continuous change is the change of the output of a function as that function's input changes. Now, that in and of itself is also pretty abstract. I think eventually you will see what I'm talking about, but I promise you, continuous change isn't the bogeyman that it might look like right now. I think you see continuous change all around you, constantly. And if I were to just pick one little example of continuous change that you see, likely on a daily basis, it is whenever you're in a car and you look at the speedometer. Maybe you're not in the driver's seat, but you can at least see. The speedometer tells you what velocity you're traveling at any given moment. And in America, it is miles per hour. Miles being a unit of measurement, measuring like distance, and hour being a measurement of time. Oh, I was writing hour. No, it'll be a measurement of time. Now, to any people who have taken like physics, distance over time being a rate might ring some bells, but for our calculus people, that's not really necessary. Let's just talk about it. In the context of our car example, let's say it took you 50 miles, and it took you 1 hour to drive that 50 miles. Another way of writing that would be to say that you started at 0 miles, or your trip had started when you started driving. When you started driving, your trip had started as well. So you start at 0, So essentially, you have a 50 miles change in the amount of distance that you traveled over an hour's worth of time. That perhaps travel might not be the most, you know, usable word at that sentence, but I suppose you are traveling through time. You have a 50 mile per hour average velocity along that interval of time, that single hour. Now, to anybody who's watched this, who has done algebra before, that little thing right there might be familiar. It might remind you of slope, which, if memory serves, is y2 minus y1 over x2 minus x1. x1 and y1 and x2, y2 both being, I'll put y2, I guess, but they're both, random coordinates. And this m shows you the slope of a line connecting these 2 points. Now, I'm going to actually draw that out for you. Let's do a nice little XY plane right there. And we'll give ourselves some point A and some point B. And actually, let me define y as a function of x, or f of x. And we're going to say that this point would be a, f of a, and we'd say that this point is b, f of b. And that we are trying to find the slope of a line connecting those 2 points. All right. So how do we do that? If m is equal to y2 minus y1 over x2 minus x1, we would have our y2 be f of b and our y1 be f of a, because f of b is to the right of, not f of b, our point b is to the right of our point a. So we'll have an f of b minus f of a, those little values corresponding to y2 and y1 respectively. And then we have b and a, or x2 and x1, would be b minus a. That's simply just the slope of a line connecting our points A and B. Another way, perhaps, of thinking of this would be to say that this, little area right here, let me draw 2 lines. This area is an interval, and we would say that is an interval from A to B, right? Because we have our x values A and an x value B. A and then B. Now, on this interval of A to B, the average change that is happening in our output with respect to our input, I know I'm getting a little wordy, but hold on. Our average change in our, output with our respect to our input, which is our x, or, as you might have heard it, rise over run, is considered the average rate of change. What? 1 second. I'm not going to write it out then. The average rate of change, AROC. That is that, or it is the slope of a line connecting points A and B, or more accurately, it is the average rate of change that our function x experiences on the interval A to B. Now, well, that's great. We're not always going to have nice little functions that perfectly connect those 2 points as a single line. More often, let me erase all this. More often, you're gonna see curves. And let's draw that same thing right there. X and Y. And we still have our points A and B. But instead of a nice little line connecting those two, we're going to put some random curve like that. And it just does whatever it wants to the right of our plane. Now, while we know that our average rate of change is that little line right there, that f of b minus f of a over b minus a, we also know that this is not super accurate. I'm going to put that back down there, y equals f of x. For our interval of a to b, while the average rate of change does give us a good idea of what's happening, our output is generally increasing along this interval. You can see that along maybe this subinterval, our rate of change in our output is increasing at a faster rate than our average rate of change, and on this interval it's actually just straight up negative. The change is decreasing. So while our aroc is a good estimation of what's happening on an interval of a to b, it's not as good of an estimation as we might want if we're trying to be super specific about it. In fact, let me erase this once more. Sorry about that. And let's give some arbitrary point C. If this is A and this is B, oh, that was awful. But we have A and B. Gonna put that down there. A and B. We give ourselves some arbitrary point, C, f of C. How do we find the exact change that our function is experiencing at that point C, f of C? Or, perhaps we could call it the instantaneous rate of change, or the iroc. How would we, write that out? What I would do is I would modify our, let's stop using M, we're adults now, we use aroc. Let's modify our aroc, and let's actually, instead of having such a big interval of, A to B, let's have a much smaller interval, really, really small, like that. And then we might have a better idea of the exact amount of change that our function is experiencing at C, f of C. Now, one way to represent that would be to write a limit. Now, a limit, I will upload a limit video in the future, but essentially a limit is the value that a function approaches as its input approaches some value. Our input is going to be C, right? So our x will be approaching C, and we can write that x, our f of x, minus our f of C over x minus C. And I know that parentheses is kind of messy, but yeah, it's f of x minus f of C over x minus C. That little point right there is C. And if that point there is C, then some arbitrary x value to the right of it is slowly but surely getting closer and closer to our C, and we can say that as the x value is approaching C. And now while this does give us a much, much more accurate understanding of what is happening at C f of C in terms of the amount of change that it's experiencing, it's also a little bit more difficult to calculate, because you have two different things to consider. You have an x and a c. What I would do is I would actually write it as one variable. Instead of having a c at the bottom, let me actually erase all of this. We're going to say, we know that our iroc at our point C f of C is the limit as x approaches C of f of x minus f of C as x minus C. We can instead write x as some, C plus some random value h. I'm guessing like y. So you remember on our curve it was like that, right? And there was a C right there. I'm gonna draw a little circle, and I'm gonna, zoom in much, much closer. Perhaps closer than is, possible on a microscope. We're gonna say that C is right there, and we're gonna say that C plus H is right there. And then C. C plus H is simply just this little distance right there. It's this random, very, very small distance that will give us a much, much more accurate idea of what's happening on our point C, f of C. Because if we shorten our interval from A to B to a much, much tighter C to C plus H, we have a much better idea of what's happening at any given point. So, with our newly equipped x equals C plus H, we're going to write that down. We have the limit as C plus H approaches C, because I'm substituting C plus H for x, of f of C plus H minus f of C over C plus H minus C. Okay, now we can definitely, simplify that. And that's what we're going to do. C plus H minus C, they have, some C's in common. So that will only leave us with the H. But this C plus H approaching C, we can treat this as an equal sign. But I'd actually like to show you, using that example that we just did, if we have this line right there, and this is like some function that's super, super like zoomed in to the point where a curve actually looks like a linear function, we have C plus H. If our C plus H is getting closer to our C, you can actually say that our H is getting closer to 0. Because if H is, to the right, it is some positive distance. What am I doing? It is some, positive distance between that little subinterval from C to C plus H. We can say that H is approaching 0 because this distance H is getting smaller and smaller as we get from C plus H to C. So, if C plus H approaches C, we can instead write that as H approaches 0. Now, let's put it all together. We can say that the instantaneous rate of change that our point C f of C experiences is the limit as c, the limit of f of c plus h minus f of c over h as our h approaches 0. I'm hoping that you see that is the instantaneous rate of change. That is our iroc. And I'm hoping that you can see how our iroc developed from our, our slope, our m, then it went to aroc, then we went to iroc. And I'm hoping that through this, you have a good idea of where that instantaneous rate of change comes from. Because, dun 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 dun, the derivative is another word for the instantaneous rate of change. The derivative is the exact amount of change that our function will experience at any given point. And while we do have c, if I were to generalize it past our interval of a to b and to make it applicable to any x value, instead of writing c, we're going to have x. You remember it was c plus h minus f of c over h. If we were to generalize this, this would be, the limit as h approaches 0 of f of x plus h minus f of x over h. I just substituted, x for c, because while we do love our friend c f of c, there's a bunch of points, and while c f of c is special, we do want this to be a little bit more general. This is called the derivative. The derivative. Let me write that very poorly. The derivative. And the way to write out the derivative, because you don't want to do all of that every single time. I was trying to circle it, but you don't want to do all of this every time. So the way that we write the derivative, well, there's way too many ways to write the derivative. We can say that, y is a function of x. We can write the derivative of that function in so many ways. We can write it as y prime. This is considered prime notation, and prime notation also is f prime x. There's also d dx, or the derivative d with respect to x. I think I mentioned that at some point, but it is the derivative or the instantaneous rate of change of a function with respect to x. And d of x is actually not using our y. That'll be like x squared plus some random stuff, but there's no y's in here, at least not yet. dy dx is a way to express the change in y with respect to x, and that will fall with that one. Like all three of these ones are ways to express the derivative of some function with respect to x if we define that function as y equals f of x, or we explicitly defined y as a function of x. Now, I could, you know what, I feel like I'm, a bit slow right now, but hey, that's the point of giving an arbitrary time limit in the title. I don't have to know how much time I'm going to be talking. We're going to do an example. We're going to do, that was nothing. We're going to do the limit as h approaches 0 of f of x plus h minus f of x over h. We're going to do that formula for x squared, or we're going to set a function y equals f of x, and we'll say that f of x equals x squared, and we're trying to find f prime x. F prime x. Okay, so I'm going to draw very poorly again a straight line and another straight line, x and y, and I'm keeping this positive, but obviously the x squared function goes out like that, but for our purposes we're going to do only in the positive. It'll look somewhat like that. If this is our point 0, 0, then if x equals 1, then 1 squared is 1. And if x equals 2, our 2 squared would be 4. And on, but it is a parabola. Now, if we were to try and find f prime x, we would plug in our x squared. Well, we'll plug in our x plus h's and all that good stuff. But we would have a limit as h approaches 0 of f of x plus h. If x is our input into f of x, then f of x plus h is quite simply x plus h squared minus f of x, hey, it's just x squared over h. Now, you can pause that, write that down. Gonna erase all this. We have our limit as h approaches 0 of f of x plus, not f of x plus h, we just defined that. We said that was x plus h squared minus f of, what is wrong with me today? Okay, it'll be minus x squared, as we said previously, over h. Now, if you've done, algebra, you would say that x plus h squared is the same as, let me write that, limit as h approaches 0 once more, x squared plus 2x h plus h squared minus x squared, we're keeping that from the top, all over h. Now, I'm hoping that anybody who's watching this video has the prerequisite algebra knowledge to understand how x plus h squared came to x squared plus 2x plus h. I mean, I could do it pretty quickly, but x plus h squared is just x plus h times x plus h. And if we were to FOIL it like that, and then that, and then that, we would have x squared plus xh plus xh plus h squared, x squared plus 2xh plus h squared. And I'm hoping that everybody's watching this knows why some binomial squared is like a squared plus 2ab plus b squared if it was a plus b squared. But, now that we've done that, we have two things that we can immediately, subtract from one another. X squared minus x squared is just going to be 0. So we have the limit as h approaches 0 of 2xh plus h squared over h. All right, let's bring that up to the top, and we will, factor out the h on our numerator, and we will say we will say that 2xh plus h squared is the same as h times 2x plus h, and then all over h, and then divide that, or cancel it, I suppose. We would have the limit, that is h approaches 0, of 2x plus h. And now, if you've done limits before, which if you haven't, this video is probably not making much sense, but if you have, you know that we can directly substitute our h for our 0, and then we'll have, since there's only one h, it'll be 2x plus 0, or 2x. Let me circle that. Now, you might not understand why we did that, but I'll show you. I hope you got all of these steps. But let me get all that off. I'm gonna draw yet another xy plane. Hope you're not too sick of them by now. X and y. I think I'll actually draw the full. No, I'll just do this again. Okay. I'll draw the full x, both negative and positive. And draw our full y, both negative and positive, even though, you know, for a squared function, you can't have a squared number that is negative, except for, you know, imaginary numbers. So let's just draw that out. It would be like that, right? That wasn't too bad. So this is our function, y equals x squared, and, you know, y equals f of x. And then we're trying to find, I don't know why it keeps doing that, f of x, and we're trying to find the derivative of f of x at x equals 2. That's the way you would write the derivative of a function at a specific x value. So now that we've done that, let me pull up my pen again. We're going to put our 1, 1 somewhere around there, right? And, you know, bang, and that'll be like a 2. And this isn't going to be proportional, but that would be about 4, because x squared, if x is equal to 2, then 2 squared is 4. If we're trying to find the slope of a line that just touches it, let me try and draw that slightly better. But if we were to draw a line that, God, drawing with your hand is difficult, okay? I'm going to use that as my excuse. There. The slope of a line that is just touching that would be, if we have f prime x is equal to 2x from everything that we've done, then f prime 2 is equal to 2. What does that mean? Now, we have the instantaneous rate of change at x equals 2 of our function y equals x squared. But that's all just words. What that really means is that the slope of a line that just touches 2, 4, the slope of that line would be 4. That line that just touches x squared at that one point is called the tangent line. The tangent line, that line that I drew, gonna extend it out. The tangent line, while not super important to us, oh, it is super important to us, but right now we're not going to talk about it too much. Essentially, it just shows you what the slope of a line that just touches one point would be. And I wish I could be more specific with what just touches mean, but honestly, there really isn't much more to say, at least at this point. So the tangent line, 2x squared at point x equals 2 and y equals 4, the slope of that would be 4. That is saying that at that point that we have said quite a few times now, the instantaneous rate of change on some infinitesimally small interval that's approaching to the instantaneous rate of change along that super tiny interval would be 4. And that's very useful. It tells us exactly what the rate of change is at that point, tells you the general behavior of that point in relation to the graph, and it tells you quite a few more things that you're probably going to have to know. But yeah, that's a worked example of what the derivative does and what it looks like if we write the derivative as the slope of a tangent line, because our m equaled 4 for that little line that I drew. I know I'm kind of, hurrying past that one, but I do need to actually talk about some of the stuff that I want to talk about. So let's start. I could do more worked examples showing you what I just said about how the derivative of any function using that limit that we've been talking about, how the derivative of any function using that limit is simply the slope of a tangent line just touching some specific point. But honestly, I don't want to do that. And I'd rather show you some rules of derivatives. I will do some worked examples if there's, some demand to do such. But let's first talk about how to differentiate sums and differences and, products and quotients and all sorts of stuff of two separate functions. I'm going to use f of x and g of x as two separate, fully distinct functions of x. And if I was to try and find the derivative, I'm going to actually use that. Remember, if y equals f of x, I could write this as y prime or, f prime x. Y doesn't actually have to be y, it could be the full-on function. Like, remember our function f of x equals x squared. I can write y prime as x squared prime. And that's what I'm going to do. F of x plus g of x prime, using that prime notation. So now that we've done that, how would we figure out what this is? Well, we're going to have to plug it back into our ever-present definition of a derivative. It is the limit as h approaches 0 of f of x plus h minus f of x over h. But since we have f of x plus g of x, if our input for f of x and g of x, if that x value is x plus h, then our limit right here is actually going to look like this. It'll look like f of x plus h plus g of x plus h minus, and we're just going to keep our x's the same. If we were to write this for x, we would say that would be f of x, oops, almost forgot that parentheses, plus g of x, put another parentheses, all over h, because that's just going to stay the same. Now, this looks a little chaotic, But we can bring our f of x closer to our f of x plus h, and we can bring our g of x closer to our g of x plus h. And I think it might be a little bit more familiar. We're going to keep that limit as h approaches 0, and we're going to write f of x plus h minus f of x plus g of x plus h minus g of x all over h. Now, I'm hoping that you all write that down. I'll give you a second to pause. And with that, we can actually split apart that function using what we know about fractions. We can split that limit into two limits, and we can write that f. We can write that limit as h approaches 0 of f of x plus h minus f of x plus g of x plus h minus g of x all over h. We can split that into two parts right there. They're not like multiplied together. I'm just, splitting them into two limits. I can write that as the limit as h approaches 0 of f of x plus h minus f of x over h plus the limit as h approaches 0 of g of x plus h minus g of x over h. And now, that's perhaps slightly more easy to understand. If we look back at our definition of a limit, that is exactly that. So we're going to say that that is saying f prime x, and even though our original definition of a limit uses f, g is still a function of x, so we can say that this right there would be g prime x, and don't forget that plus. Now, that was a relatively simple proof showing you why the derivative of a sum of functions is equal to the derivative of those individual functions added together, or f of x plus g of x prime is equal to f prime x plus g prime x. And now, I'm going to encourage you to do that if you want, to prove why the inverse is also true. F of x minus g of x prime is equal to f prime x minus g prime x. That is also valid, and I'm hoping that you can go back and, copy down the steps that I've put and then reapply them to subtraction. But essentially, these are like sister proofs, They both have the same mathematical operations, and they both come out to relatively similar outcomes. But now, I'm going to do a slightly... I'm actually not going to do the more difficult proof just yet. I hope you got both of these little rules down. These are called the sum and difference derivatives, or derivatives of the sum and difference of two functions, whatever. But they're just saying that if you add two functions and then you take the derivative of that addition, that's just equal to the derivative of those individual functions added together. Now I'm going to do another somewhat simple proof to look at, let's say C is some number. It is a constant. It could be negative, it could be positive, but it is a constant. How would we find what the derivative of a constant times our f of x is equal to? Well, we're going to look back at our trusty definition of a derivative, and we're going to say that we're going to go back to our limit as h approaches 0. If we have c f of x prime, our input x being x plus h, that is just going to be c f of, well, I could write it together, I guess. You can write that as c f x plus h minus c f of x, because, if x is our input right there, then it's just going to be c times f of x all over h. So, what can we do with this? Well, we can apply some factoring. We can take out our c. That'll be c times f of x plus h minus f of x all over h. And if you've ever done limits before, you might know that one of the properties of a limit is that we can pull constants or things that we're trying to factor. We can pull them out in front of the limit. So, might be running out of room here, we'll see. We'll pull our c, our constant, to the outside of our function, or our limit, and we'll have f of x plus h minus f of x all over h. Now, if this hasn't been drilled into your head already, I must not be doing my job. But that looks like our trusty friend, the definition of a derivative. So, we're going to write this again as c f prime x, if all of this stuff is equal to the derivative of f of x, or f prime x. So all of that was, a nice little proof to show you why the derivative of a constant times a function, it can simply just be, the constant getting pulled out as the function gets differentiated. So yeah, that's a nice little rule, and I'm hoping that you understood why that was. But that can be helpful, pulling out specific constants that you need to get pulled out. But this rule is, actually, you know what? I'm going to do another somewhat simple rule real quick. We're going to do the derivative of a constant. This one, I promise, is easy. The derivative of a constant, while it is a function, it is a function of x. It doesn't take, I shouldn't say that it doesn't take any input. I should just say that the input that it takes does not affect its output. So, if our input was x plus h, our c right here is pretty unbothered by that. It's just going to still remain c, as the limit as h approaches 0, it's going to be c, because regardless of whatever x value we have there, if it's x plus h, if it's, x, like 3x or 2000 or whatever, it's always going to be c. So c is right there. And again, if we use our x, our c is unbothered. It will remain a c all over h, and then we have the limit as h approaches 0 of 0 over h, or the limit as h approaches 0, I'm sorry I'm writing so slanted, of 0. It's going to be 0. So let me erase all of this again. All of that, I probably should have left you a little bit of breathing room to process that and or write that down. But essentially, that's the reason why the derivative of a constant is 0. If you look at some, let's say that was y equals 1, and we have our x-axis and our y-axis. There is no change happening in our output as our input changes, so the average rate of change, even on some super tiny interval right there, it's going to be 0. There's nothing happening in terms of the output changing. So yeah, we've gone through a couple rules that are pretty important. I'll write them down one last time. F of x plus or minus g of x. The derivative of all that is just f prime x plus or minus g prime x. And then c f of x prime is equal to c f prime x, and then c prime is equal to 0. That's just a couple of random rules that you're going to have to use, but they're pretty simple. This next one, while it is kind of still a pretty simple proof, it's going to be a little bit more complex than what we've been doing so far. If we're trying to find the derivative of f of x times g of x, what would that be? So, with that lovely derivative that we need to do, this one's going to be slightly more complex. We're going to keep using our definition of a derivative that we've seen at least a dozen times by now. The limit as h approaches 0, if our input is x plus h for both of those, we're going to plug in f of x plus h times g of x plus h, and it's going to look like that. And then we're going to plug in x. It's just going to look like exactly what we've been doing. F of x, g of x, all over h. What do you think we can do with that right now? I'll give you a second to think about it, but what we're going to have to do is we're actually going to have to break this into... So what we're going to have to do is we're going to actually have to add in and subtract something. Something that might seem a little random, but I'm hoping eventually you might see where it comes from. Well, we're going to have to add and subtract. Let me put down what we already have. F of x plus h times g of x plus h. We're going to add and subtract 1 f of x plus h times g... I've run out of room. Let me actually erase all that. just take a good look at what we have so far. We're going to have the limit as h approaches 0 of f of x plus h times g of x plus h, and we're going to add and subtract 1 f of x plus h times g of x minus that same thing, because anything minus itself is going to be 0, and we don't want to change the function because that would alter our outcome. So we have this minus itself minus f of x g, again running out of room, I need to write smaller, but it'll be g of x. Okay. Alright. Now we're gonna put that all over x, and now this is gonna take quite a bit of understanding of the limit properties. Again, that will be in another video, but we can break this apart. We can factor out some x plus h's and some not x plus h's, some f of x plus h's, and we can write this limit as the limit as h approaches 0 of f of x plus h times, I'm going to actually put some parentheses because we're going to do a similar thing but very different. X plus h minus g of x all over h. That might seem like quite a few jumps, but we're just factoring out this g of x plus h and this g of x right there. And since they have this, f of x plus h common right there, we can take that f of x plus h out, and we'll keep our g of x plus h and our g of x. And that would really aid in our calculations because, as we know, this is the derivative of g of x. But I'm getting, again, a little ahead of myself. We have that, and then we also have the same thing, but opposite. We have the limit as h approaches 0 of g of x times f of x plus h minus f of x all over h. Again, I know that looked like a bunch of jumps, but I factored out. So I'm going to scribble this out. We did that one, and we did that one, and those two corresponded that one. So we're going to factor out our f of x plus h and our f of x. And since we split our fractions, because, this whole thing itself is one giant fraction, but since we split that, we have our f of x plus h, our f of x, and our h, and thank God there is a minus right there, so we can simplify this further. We factor out our g of x from both, and we bring it out to that front right there, g of x, and right here, as I'm hoping we've all seen a couple times by now, that will be f prime x. So, again, that was a lot. Whoops. Just, what is happening? Okay. Just, copy down all of that, and I'll erase this stuff. Okay. So, Now that we have all that, we can actually write our, remember how it was, like f of x plus h times our g of x plus h minus g of x all over h, and we were doing the limit as h approaches 0 of this whole function. If you've done limits before, you know that if you are multiplying two things, you can actually split them into two different limits with the same value that is approaching. So we're going to have the limit as h approaches 0 of f of x plus h times that same limit value that we're trying to approach, h approaches 0, of g of x plus h minus g of x all over h. Okay, and we are going to add, if you remember, we're going to add the limit as h approaches 0 of g of x, because remember, it was g of x times f of x plus h, the limit as h approaches 0 of f of x plus h minus f of x all over h. It'll be the limit of h approaching 0 of g of x times one more limit as h approaches 0 of g of x plus h. God, what am I on? It'll be the limit as as h approaches 0 of f of x plus h minus f of x all over h. Now, these two are already pretty familiar. They're both the derivative of their respective functions. That one on the top, that would be g prime x, and that one on the bottom will be f prime x. But our limit as h approaches 0 of f of x plus h and our limit as h approaches 0 of g of x might be a little bit more elusive. We're going to do our direct substitution. We have f of x plus h. We're going to substitute our h for our 0. That will give us f of x. And then this one, like our constant c, h is not an input. Well, it doesn't change the output, is a better way of saying it. So the limit as h approaches 0 of g of x is just going to equal g of x. Now, take a second. You know that this is g prime x, this is f prime x, this is f of x, and this is g of x. So let's organize our thoughts just a tad bit. Okay, wait 1 second. Okay, there it is. We have f of x times g prime x plus g of x times f prime x. Oof. If you remember, that was supposed to be the derivative of f of x times g of x. So I'm hoping that maybe like 70% of what just happened was understandable. That's the reason why the derivative of a product of functions is equal to that. And you might see this as, this might actually be written for you in some textbooks as, let me finish this. uv prime is equal to u prime v plus uv prime. While that might be simpler or even easier to remember, I think this might actually be a little bit more detrimental to you, because I think that having x being explicitly defined as the inputs for your functions, I think that makes it slightly more easier for me, at least, to understand why the derivative of a product of two functions is what it is. U and v aren't explicitly defined as functions of x, and while that might be useful for, calculus in the future when you're probably not going to only be using x, I think that for our purposes, this, one right there, is a better, way to show the derivative of a product of functions. Now, I know you're getting a little bit sick of looking at only f of x and g of x, but we have one more to go,